So we have our definitions of instantaneous and average acceleration, and now we know that things fall at a uniform constant acceleration of 9.8 meters per second squared near the surface of the Earth. So we're ready to do some kinematics, right? So we're going to do kinematics with the assumption of constant acceleration. Before it was constant velocity, now constant acceleration. And the problem we're going to work around now is that I throw a piece of chalk down at 2 meters per second in frustration, right? And then how fast does the chalk go? So this one looks something like this. I have the chalk here, and the students all bomb the exam. So I'm like, ugh! Like that. Ah! So how fast did the chalk go after a half second? Actually, I think at a half second it had shattered, but let's pretend it kept going at a half second. So the way we would do this is derive some kinematics from our definitions. And it's going to be just like before. We're going to assume that if everything is constant, if the acceleration is constant, then the average value equals the instantaneous value. And that's going to let us write an equation very similar to velocity as well. The instantaneous acceleration equals the average acceleration equals the change in velocity over the change in time. So we want to think about this one being equal to that one to get equations that look kind of like what we're used to. So we're going to say A equals the final velocity minus the initial velocity over, and remember delta t was t final minus t initial. T initial is usually 0. T final, we just call it t, so we can say over t. Right. Turn that around, solve it for the final velocity, and say v final is v initial plus acceleration times time. And that is yet another important kinematics equation. This is how you figure out how fast something is going after it is accelerated for a while. I don't know, maybe this one has a street name that v equals at, if you're being simple. That was just the velocity you got to if you started at 0 without all the vector notation all over it, right? So you may have seen this one before. Let's solve our problem then. So it's pretty straightforward here. How fast did it get going? So VF is what we want. And if I threw it down at 2 meters per second before I released it, right when I released it, 2 meters per second was its initial, right? So that's equal to 2 meters per second plus AT. So A, we know, is 9.8. I'll put units, I guess, meters per second squared. I'm making it positive because we're thinking of down as positive. If we thought of down as negative, I would need to put a negative sign here, but let's think of down as positive. Here we go. And t is 0.5. All right, seconds. So we solve that, and we get a half of 9.8, and we add 2 to it, and it's 4 point, whatever it is, 6.9 meters per second down. And it's a vector because I put down, we'll say. So pretty straightforward to plug in, but always remember this one, but always remember, more importantly, that it is only for constant acceleration. Now we need to find the change in position under constant acceleration. We did velocity, now let's do the more difficult case of position. It's going to take some calculus, so just bear with me. If you hate calculus, you could skip this lecture. I'd suggest you watch it. The next video, I'll do it completely graphical, and maybe you'll like that better if you hate calculus. If you love calculus, this is it. Here we go. Get excited. Here we go. So what we're going to do is we're going to derive it for an object that's accelerating, constant acceleration. We're going to look between time 0 and time t, and in that time, it goes from initial velocity to final velocity. We've kind of already done that. But also, it goes from an initial position to a final position. Right? So at time t equals 0, it's at vi and xi. At time t equals t, it's at vf and xf. That's the plan. So let's start like this. It actually all starts with the instantaneous velocity being the derivative of the instantaneous acceleration being the derivative of the instantaneous velocity. And then we just rearrange this. We bring the dt over here, and we say dv, the little differential change in velocity, is just the acceleration times whatever differential change in time you do. Right? That's just the differential version of v equals at. And what we're going to do is integrate over the interval we're thinking about. integrate from 0 to t. Integrate just means sum up. We're going to add up all these little delta t's, dt's, and apply them multiply them by a to see what the new v is. So you'd write that in the math formalism would look like this. You'd integrate dv from vi to vf, right? And that would be equal to the integral of a dt from 0 to t. Right? Your limits have to match whatever your differential is. Here the differential is v, so they're v's. Here the differential is dt, so they are t's. So if we integrate dv, if you know how to do calculus, the integral of dv is just v. Right? So v evaluated from vi to vf, well, vectors everywhere, that's equal to a dt, the integral of a constant times dt is just the constant times t. So that's a t integrated from 0 to t. All right, and then what do we got to do? We just got to apply the bounds, and you'd get vf minus vi. So plug in vf for v is vf, minus plug in vi for v, vi, equals at, plug in t, you get at, minus plug in 0, you get nothing. So this part is just at, right? And then you see, that's basically what we just did, right? That's the final velocity is the initial velocity plus at. That's the calculus version of that other board that we did. So if we want to get to position, now we go to v, the instantaneous velocity is the derivative, the time derivative of the position, dx dt. Same thing, turn it around and say dx equals v dt. All right, that's just d equals vt, really, the old equation you know and love. And what we're going to do is integrate it. And in this case, I could have left myself a little more room. We're going to integrate dx from where? xi to xf. And v dt, we're going to integrate from what? From vi to vf. I'm sorry, we're doing d, from 0 to t. Integral over t. Right, okay. Now, let's see. The left side is easy to integrate. The integral of dx is just x, and we evaluate it at xf minus xi. Right, so this just becomes the final position minus the initial position. Right. And now, what about this integral? We just have a v there. Is it just vt? No. Right, we just stick a t on there when there's a constant. Right, this was a 1 times v, or 1 times x. Here, a was a constant, so it just became at. But v is not a constant. V is changing in time. And we know how it's changing in time, over here. Right, so this is v at some time t. That's actually what this was. This is the v final, is v initial plus at, where v final really could be at any time. V final was the velocity at time t. So we can actually plug that little expression into here. It's the integral from 0 to t, and for that velocity expression, that's really a function, we write v initial plus at dt. Right? That's where it gets interesting, if that's interesting to you. I hope that it is. So now we take the integral of that. Right? So we have the final position minus the initial position, also known as the displacement, equals, let's see, so that's integrate this part. Now that is a constant. Right? This velocity, this is the initial velocity. It's not a function of time. It's a constant. So the integral of that is just vi times t. And then plus at. The integral of at is, bring the t up to squared, divided by the 2, is 1/2 at squared. And yeah, technically, we've got to evaluate that from 0 to t. It kind of already was. But just to give myself another step, I'll put the final position minus the initial position, evaluate all this at t, vit plus 1/2 at squared minus, evaluate it all at 0, 0. Okay. And then there you have it. So this is the final equation. We could move the xi over here to get sort of the most normal form. The final position is the initial position plus vit plus 1/2 a t squared. possibly the most famous equation in all of simple 1D kinematics. But it only applies if you have constant acceleration. And to use it, you need to know if maybe you have some constant position or initial position and some initial velocity. So next I'm going to show you another way to get this, and then we'll look at how you can use it a little bit. So we derived the position for constant acceleration kinematics using calculus, and now I'm going to show you how to do it just with graphs. Now that really calculus is just graphs. But before I do, there's something I have to get off my chest. I've been teaching in this room for about 7 years, and I have been staring at these. Hiding in a drawer under this bench are these two puppets, and they've been haunting me for 7 years, and I do not know why they're here. I don't know what they're for. I'm imagining some sort of harassment seminar. I don't know, but it really bothers me. So if anybody can fill me in on this, I'm just going to put them back and try to pretend they're not there. Now, here we go. So let's think then about these graphs. So we're going to do the same problem, and actually I'm going to throw it again because I want to see acceleration with a constant initial velocity, right? So I'm just going to do that again. Okay, that's the problem we're looking at. So it's the case of the chalk that started at the origin and went down, where down is the positive x direction. And we gave it even an initial velocity. Right? So to do this with graphs, we need to draw the graph. So let's draw the position versus time, x, the velocity versus time, v, and the acceleration versus time. So we know it starts with an initial velocity, so I'll give it a little bit of a slope at the beginning and then have it go up like that. We know it starts with some offset from here because it had an initial velocity, and then that velocity continued to increase due to acceleration. And we know it had a constant acceleration because everything near the surface of the Earth has a constant acceleration. And we know we're asking ourselves, how fast does it go after it gets to some time t? So we could say to this point t. Ran out of room there. There we go. So we're going to solve this graphically. But there's one thing we got to sort of know, we got to remember. And one thing is we know that if we go this way, we're taking derivatives and slopes. Right? When you have position versus time and you want velocity versus time, what do? You take a derivative. Or, if you like graphical analysis, you can say the slope. Right? If you want to know the velocity from this thing, you take the slope of this curve, and it's equal to the velocity. The slope is increasing. That's why the velocity is increasing. Same thing. Every time you go down, that happens. We could go down from here to here. And again, you take the derivative, which is just the slope. Right? If you have the velocity time graph, you take a derivative to get the acceleration. And here you can see it's a straight line. Its slope is constant. Acceleration is constant. Right? You can go the other way, and this is getting a little more calculus-y, is you can go and say, what is the change in velocity based on this graph? You can go this way. To go that way, you take an integral. An integral is an antiderivative. Going this way is derivative. Going this way is the integral. Here I'll say the change equals the integral. The change in v equals the integral of the a. Or you can think of it as the area, the famous area under the curve, right? So you learn that in calculus, that's kind of what an integral is. It's an area under a function. So the change in v is the area under the acceleration curve, and the same thing happens here. It's really just math, so it has to be the same. Here also, the change in delta x, the delta x, equals the integral of the velocity versus time curve, which is also just the area. Okay? So let's see if we can use this to derive the kinematics equation. Sounds crazy, but let's just see what happens. Let's find delta x. All right, but from 0 to t. This is the interval we care about. Delta x, basically x final minus x initial, that domain right there, equals the area under this curve. So this is a lopsided trapezoid. I don't know my geometry anymore. So this is something, but I know what I can do is break it up into a rectangle here and a triangle there. So I just need the area under those two curves, and it will be equal to delta x, right? So let's pick one. Let's do this one first. That one's easy. Let's see. It's t on this axis. All right. Let's see. That's t. And what is it here? That's vi. Remember, it started at a height v initial. So the area of that box is vi times t. Okay, that's not so bad. And now we need the triangle. What's the area of a triangle? It's 1/2 base times height plus 1/2. And what is the base? The base is t, all right, 1/2 t. And what is the height? The height is the change in v. Right? The height is delta v. But what is delta v? Oh, delta v, we've got to do this again. The change is the integral. It's the area under the curve. That's delta v. What's that area? A times t. A t. And delta x is fx is x final minus x initial. So x final, I'm sorry. So x final, bring the x initial over, x initial plus vit, and this is plus 1/2 a. Oh my God, look at that. It's the kinematics equation the whole time, straight from geometry. Pardon my lack of vector notation. I decided for this one geometrical derivation we didn't have to use vectors. But you can see it worked because it's the same thing. That's what slopes and that's what integrals really are. Now you won't always have simple constant curves like this. We still need to do calculus for other kinds of problems, but for these, technically, this is all you need.